Hello again. Today we're going to be talking about parametric equations and how we can use and calculate velocity and acceleration with parametric equations. So we need to remember that parametric equations are written as an x equation and a y equation where both of those variables are expressed in terms of t. So we can write that as a vector where the first function in that vector is x of t and the second one is y of t. Those equations will give us the x and y position of an object at any time t. So for example, if I have x equals t to the 2/3 and y equals sine t as t goes from 0 to 10, then I get a graph that looks like that. Now the arrows show the direction of the path. And so each of those dots is separated by 1 second. So the first dot is when 1 second has passed, and the second dot is when 2 seconds have passed, and so on. So I see where the particle is going, but I also know when it's going to reach each of those points on the curve. So velocity is going to represent speed in a specific direction, just like it always has. But with parametric equations, the particle is no longer traveling along a single line like it has in the past. So velocity can't be expressed as a single number because it has direction associated with it. So what we're going to do is we're going to measure the velocity of x and y by taking the derivatives separately, taking the derivative of the x expression and the y expression separately. So I will end up with a velocity vector just like I had a position vector before, but the velocity vector is simply the derivative of the x expression and the derivative of the y expression. So if I have the same example that I had before, it's still on the graph to the right, x equals t to the 2/3 and y equals the sine of t. So the derivative of x is going to be 2/3 t to the -1/3, and the derivative of y is going to be the cosine of t. So now I can calculate the horizontal velocity and the vertical velocity of a particle at any time t. So if I wanted to do that, let's say I wanted to figure it out for this point here where t equals 3, then I plug 3 into the expressions that I have for the derivatives of x and y, and I get 0.462 and -0.990. If I have a positive x derivative, then that means that the particle is moving to the right. And if I have a negative y derivative, that means that the particle is going downward, which you can see from the picture that both of those statements are true. So here's another example. Let's say that x equals the sine of t and y equals the cosine of 3t as t goes from 0 to 5. What's the velocity when t equals 4? Well, it looks like the graph at that point, the particle is going to the left and it's also going up. So let's see if that's true. X prime of 4 should be negative and y prime should be positive. So let's make sure that both of those things happen. The derivative of x is the cosine of t. So at 4, the derivative of x is going to be the cosine of 4, and I'll need a calculator to figure that out. That is negative 0.654. And the derivative of y is going to be -3 times the sine of 3t. If I plug in 4, that's -3 times the sine of 12, and a calculator will tell me that that is 1.610. So I did get that the derivative of x was negative and the derivative of y was positive at t equals 4. So my answers do make sense. And so the velocity vector is -0.654 and 1.610. Now for acceleration, it's probably going to make sense if I still have these x's and y's. Then just like the velocity vector is going to be the first derivative, the acceleration vector is going to be the second derivative of each of those, and I will keep them separate. So for this example, the velocity vector was the cosine of t and -3 times the sine of 3t. We figured that out before, and so now the acceleration vector is going to be the derivatives of those. So the second derivative of x is going to be negative sine t, and the second derivative of y is going to be -9 times the cosine of 3t. So let's see what it would be at t equals 4. At t equals 4, I just plug in my value of 4 in place of t, and I get negative sine of 4 and -9 times the cosine of 12, which is 0.756 and -7.595. Okay, so going back to our first example, if I have that x and that y, and we've seen that graph before, So for this example, the velocity vector was 2/3 t to the -1/3 and cosine of t. If I want the acceleration vector for this, I just take the derivative again, and I will get negative 2/9 t to the negative 4/3 and negative sine t. If I want to figure that out at a specific t value, like 4, then the acceleration vector is just going to be those expressions with 4 plugged in for t, and I will get an answer of negative 0.035 and 0.757. So nothing really new in terms of position, velocity, and acceleration. It's just that we're calculating it for x and y separately in both cases. So if you have any questions on this, please let me know, and I will see you tomorrow.